Thank you for being here. What I'm going to try to do is give you a tour of why we're in one of the most fascinating periods in computer architecture and the future of computing at this point, possibly a time that is unrivaled in terms of the potential for change since the early 1980s and the rise of the microprocessor. That starts with, of course, the very popular thing, the end of Moore's Law. In fact, now in professional groups, we don't even write the end of Moore's Law, we write EOML, and everybody knows what it means. So, but we're going to talk about that, some of the other changes that have occurred, and how we're beginning as an industry and as researchers to respond to this set of changes. So there's enough technical material in here, but you don't have to get everything. So I'll not touch all the technical details, but enough to give you a flavor of what's happening. So this is really an amazing time. If you think about what's happened in the last 40 years in terms of microprocessors, we've maintained a 40% annual increase every single year for 40 years. That means the throughput, that is the total, you go and buy an Intel processor now for your laptop or your high-end desktop machine, you get roughly 10 to the 6th times the computing power that you would have gotten 40 years ago. 10 to the 6th. It's amazing. Think about if cars were like that. You know, the Tesla would cost $1, and when you drove it, and you'd get all the way across the country on one charge, and then you'd fold it up and put it in your briefcase. That's what it would be like. Amazing. Lots of architectural innovations. Obviously, those early microprocessors were only 8 bits wide. Today, 64 bits wide. Instruction level parallelism from 10 clock cycles for every instruction to 4 instructions every clock cycle by comparison. And tremendous improvement in clock rate as well. The early microprocessors, the 8-bit ones, were around 3 megahertz. Today we're up around 4 gigahertz. So a factor of 1,000, more than 1,000 just in clock rate. Lots of things, multicore obviously. The key, of course, to doing this were two things. One we talk about all the time, Moore's Law. We talk about the ability of the semiconductor industry to year after year deliver these incredible improvements in technology. But the other piece of this that is much less talked about is another property called Dennard scaling, invented by Bob Dennard. You all have used a product that Bob Dennard invented. Namely, he invented the one transistor DRAM cell. So if you've used them, and you've used a lot of them, right? So, but he made an important observation. His observation was the power per transistor shrinks as the density increases. And that was crucial. His real observation was power per square millimeter of silicon is constant. So if you think about that, power per square millimeter. Now take one generation of silicon, the next generation, a lot more transistors per square millimeter, but the same power. Therefore, the power per transistor has shrunk, actually, meaning that the technology was making things more and more energy efficient all along. So we're at a big change point, and that change point is caused by some technology changes, the end of Dennard scaling as we've known it, the beginning of the slowdown in Moore's Law that everybody talks about, but also architectural changes. The ideas that have driven forward microprocessors so dramatically over the last 40 years are running out of steam, and they're partly running out of steam because it's an efficiency argument. It's an argument about how effectively they use power and how effectively they use silicon. But another thing's happened. You know, if you think about the last 40 years, the desktop dominated till about 10 years ago. And then all of a sudden these devices became the dominant way, and most people in the world now, when they use computers, this is what they use, especially if they're under 20. Especially, right? Especially if they don't live in the United States. This is the device they use. And the desktop has gone down in importance to be replaced by the rise of the cloud. So we've kind of changed to a different computing model, right? The edge with lots of IoT and all these sorts of things, and these big cloud things. And that's created new constraints. So we all talk about what's the effect of the slowdown in Moore's law, and one way to look at it, and this compounds the effect of what's happening in Moore's law as well as what's happening in Dennard scaling. So when you see these curves that show, this was the heyday of microprocessors. Here's the invention of RISC, first RISC machines about 1985. This giant period, 52% per year over year, sequential single processor performance improvements, 52% per year. That's amazing. So that was a hot time. Then we began to slow down as we had to go to multicore, some more slowdown, and the last few years, 3.5% a year versus 52% a year. Okay, this curve compounds the effect of Moore's law and Dennard scaling. Both those changes are built into that curve, and they're both having an effect on what's happening. So let's look at how important they are. First thing about Moore's law is there is no such thing as Moore's law. Law is theorem. Law is something that's a physical reality. Moore's law was a hope. It was a prayer that Gordon had, and he said, we could do this. And that set a benchmark for the industry. And the industry responded. Enormous dollars invested in year over year to improve those technologies. And if you look at it, we're only off of Gordon's latter projection, his 1975 projection. His first projection was too optimistic. But his 1975 projection, we're only a factor of 10 off. 10 off while we've gone through almost 7 orders of magnitude, 6.5. 10 off. 10 is not much compared to a million. Small number, right? Even compared to the last, where the gap really began to grow, which is right in this period here, even there, it's a factor of 10 versus 5,000. So that's pretty good. Yeah, it's slowing down, but not as dramatically as people might predict. Some people will show you plots of DRAMs. I pulled out the DRAM plot. DRAMs are a very special technology. They're misleading. They give you the wrong impression about what's happening in Moore's law. This is Intel microprocessors. It gives you the right impression. So things are slowing down. I should point out that there's also a cost issue here that's a bit critical. Cost is going up for next generation fabs. So the cost per transistor is slowing down even more than Moore's law would tell you it's slowing down. What about Dennard scaling? What's happening with Dennard scaling? Well, this is a curve. Here is the improvement in technology coming down in terms of feature size. Here's what's happening with Dennard scaling. You see this bump right in here. 2007, about 12 years ago, things began to take off, and then a second one about 7 years ago. And what that curve shows you is the power per transistor. It's not scaling anymore. It's not scaling the way it used to. And that creates the fundamental problem, because it means you have to think. It means that energy per computation is not going to go down the way it's gone down. So you have to think a lot more about power efficiency. And that's one of the things that's driven the market to move back and embrace some of the risk ideas from earlier on, is that energy efficiency becomes really important. And so therefore, you're trying to think about ways to optimize that, and having a simpler instruction set that's simpler to interpret, that's easier to implement, buys you energy efficiency. And that becomes a key driver if you're looking at that. Well, why do we care so much about energy? Well, we care about energy because these devices operate on batteries. And the battery is an expensive part of it. It's also the thing that, what happens when your phone runs out of charge? It's a disaster. You have to then go find some place to plug it in. You go to the airport, you see everybody looking around for little outlets to plug in their phone, and it's really a crucial thing. So battery technology, despite all the effort that Tesla, it still makes very slow year-to-year improvements. It's not, as Gordon Moore once said to me, he said, batteries are chemistry. He goes, that's what my PhD is in. It's hard. But the interesting thing about this, by the way, the LCD is the biggest consumer, but the CPU is close behind, which is really driven by energy of the CPU. And as we move to devices that are always on, when you have this device on all the time and it's tracking where you are so you can get a map or you can call Uber, then you've got a lot more battery drain. But it's also true in the cloud. This is something people don't realize. They think the cloud, oh, that's this big machine. It doesn't matter. Energy efficiency doesn't matter. It does matter because in terms of capital cost, this is what the computers cost you. That's what the power and cooling infrastructure in a big Google data center cost you. So you're paying a lot for that. And even when you amortize it, this is the power infrastructure plus you have to pay for that power. And the thing about power infrastructure is you have to pay first to buy the electricity, then you have to pay to get rid of the heat that you generate. So you're paying twice. And so it becomes a big piece of the cost. The servers cost more on an amortized basis, but that's because you replace the servers every 3 years, and power infrastructure you replace every 10 years. So, but still, it's a major factor in considering how to run a large data center. So this end of Dennard scaling is really a crisis, not because of the way machines have changed. It's also a crisis because the amount of heat we can get out of a semiconductor package goes up very slowly from year to year. So packaging technology is a slow thing. It creeps forward slowly. And we've reached what we call the thermal dissipation power limit. Namely, the chips are so hot that we can't put more power in to make them go faster because they're going to burn up. They're going to burn up. And we'll talk some more about that when we talk about multicore. But when you think about this, what that means is that architectural advances, ways to go forward, have to improve energy efficiency to match with the changes in the technology. Unfortunately, most of the techniques we've used do just the opposite. They sacrifice energy efficiency in order to get performance. Right? It's the same thing. Think about an automobile, right? You move from that nice four-cylinder engine, gets very good gas efficiency. You put the 6-cylinder and it's a little what you put in the big V8 turbo, and your gasoline efficiency, your speed goes up, but your efficiency in terms of consumption of energy in the form of gasoline goes down. It's the same problem here. And all these architectural limits are started to hit around the same time. The instruction level, what we call instruction level parallelism, which I'll say a little about. Multi-core limits, primarily arising from Amdahls Law, something invented, something discovered in the 1960s that still plagues us. And even things like caches. I mean, caches are one of the most fundamental insights in how to make machines fast, right? Build small memories, keep the data local, make them very fast, make it very easy for the processor to access that data. The problem with caches is what you want to do is make them bigger and bigger as you get next generation. As you make them bigger and bigger, they do less and less. They're diminishing returns. And that's exactly the problem we're in. So this instruction level parallelism era, which was this great era from about 82 to 2005 when we were getting 50% performance per year improvements, what we basically did was we went from these machines that had these fairly shallow pipelines to machines that had very deep pipelines. They would have 15 instruction stages in terms of executing instructions and would do multiple instructions per clock. And what killed this was not that we didn't have, that you could take the same techniques and move them forward to a new generation and improve them. And the problem was that they hit that efficiency wall. That was the real problem. And so where does that efficiency wall come from? Well, if you think about it, suppose you want to start executing 4 instructions every single clock cycle. And suppose you have a pipeline that's 15 instructions deep. So you're doing 15 pieces of 15 instructions at once. That means you have 60 instructions, what we call in flight. So there are 60 instructions that the hardware is looking at and executing some piece of at any given time. 60. The problem is, to get 60 instructions to operate on, I've got to guess which way branches go. I have to kind of what we call speculate on the code sequence. I've got to guess in my branches, and I've got to begin executing instructions as if I knew exactly what those branches were going to do ahead of time. How hard is that speculation? How hard is it to guess which way the branches go right and do the right thing? Well, when you have 60 instructions in flight, that means you have to guess about 15 branches correctly. In order to get 90% accuracy on all 15 branches, you have to have 99% accuracy on every single branch. Now, to get 99% accuracy, every program has to do the same thing, more or less. 99 out of 100 times. So that's highly unlikely. You're going to get a lot more variety. Programs are data dependent. What they might do will change a lot. And so you can't get that for really big programs. You can get it for nice little scientific kernels and small toy programs, but for big pieces of code, you're doing Google search, you're doing a big AI application, you're simply not going to get that kind of level of predictability in your behavior of your program. So this just shows you one way in which this plays out. So think about an Intel Core i7, right? Their current high-end Core architecture, basically. Because it's guessing in the branches and doing all the speculation, it periodically has a bunch of things that it does all the work on an instruction, and then it concludes, that was wasted because I guessed a branch wrong. Now, what you have to do is you have to throw out that work, it was wasted, and you've got to get the processor back to where it was before it made the incorrect speculation on the branch, before it guessed wrong. So all that energy is wasted. And this just shows you on a bunch of different spec benchmarks, standard benchmarks, what percentage of the instructions actually are completely wasted. And you see it runs, some cases it runs almost 40% of the instructions. Almost 40% of the instructions you do the work for, wasted, throw them away. Throw all the energy away and fix it up. So this is a real problem. You've hit that efficiency wall. You're in the area of diminishing returns. You're not going to get a lot more if energy is a limit. So that led to what we call the multi-core era, saying, okay, we're not going to try to make one processor run faster. We're going to try to put many processors on a single piece of silicon and get speed by letting the programmers do the work, right? The hardware guys were working really hard. They said, you know, it's time for the software people to do a lot more work here. So besides we've run out of good ideas, so we'll let the software people decide how to break this program into parallel parts that can be run in parallel. And that was the basic strategy. The nice thing about this is you go and buy a multi-core chip now. You go to buy a chip for your new desktop. You'll get 4, 8 cores in there. And somebody has to figure out how to use those. The key thing is it's nice from a hardware design viewpoint because Intel wants to come out with a next generation processor. They just say, oh, we have this many more transistors, add 2 more cores. Pretty easy design job. Right? It would be very easy if power were not a key issue. The key problem is that the energy is proportional to the transistor count, which is proportional to the number of cores that are active. So you need performance to be proportional to the number of active cores. If you want to have good energy scaling, then the amount of performance you have to get has to scale linearly as you add cores. But as Gene Amdahl discovered in the 1960s in a famous paper, that's a really hard thing to do. It's a really hard thing to do. And this just shows you this is a classical Amdahls Law plot, which shows you how, if you add processors, you add cores, how much speed up you get if you assume 1% of the program or 2% of the program or 10% of the program is sequential. That is, can only run on 1 core at any given time. That's the simplest way to do Amdahl's Law. There's lots of variations in it. But look at this. Even if you say only 1% of the code is sequential, you get a speed up of about 36 or 3840, something like that, on a 64 processor machine. Unfortunately, you pay the energy costs of a 64 processor machine, even though you only get the performance of a 38 or 40 processor machine. You've lost that energy efficiency because of this sequentialization effect that's fundamental to Amdahls Law. What's the other effect of Dennard scaling? Well, the other effect is on what we call thermal dissipation power. Namely, what happens, you put all this energy into a processor, you've got to get the heat out, right? Think of processors just the way internal combustion engines are, right? You put the gasoline in, it makes the car go, but you have to have a radiator and fan and water circulation system to take the heat out. Same thing in a processor. You put the energy in, the processor does its computation, but it generates heat, and you've got to get the heat out. The most amazing thing, if you told me 20 years ago this was what's going to happen, I would have said, you're crazy, it'll never happen. Modern processors with multiple cores turn off the cores, slow down the clock to prevent themselves from burning up. If you run them full out, they'll burn up. They'll burn up. So just to show you that, here in a 14 nanometer process, Intel's largest multi-core, E7-8890, it's a 24 core machine, runs at 2.2 gigahertz, and its thermal dissipation power is 165 watts. It's thermally 165 watts. Remember, this is a little piece of silicon about this big that's generating more energy than a 150-watt light bulb. Okay? If you pull that off, you take the fan off and put your finger on it, you'll know about it. You'll know about it. Okay. So, but notice this. If you run it in turbo mode, which is only allowed with one core, that's the high-speed mode, it can run at 3.4 gigahertz. That's the actual clock rate that the underlying silicon could run at if it wasn't power limited. If you were to run at 3.4 gigahertz, though, and you ran all the cores at that, you generate 255 watts. That processor, you turn it on, it would last about 30 seconds. And then it would melt its leads, and all kinds of bad things would happen, and you'd have to go spend another $500 to buy another processor chip. So it really is a key fundamental limit. And going forward, it's going to get worse. Because of the slowdown in Dennard scaling, when you look at it, for example, a 7 nanometer process, you'll get about 64 cores. In power unconstrained mode, they would run at about 6 gigahertz, and you would have about a 365 watt chip, more than double today's processors. Power constrained, you'd still have a 250 watt chip if you constrained it in to the same power consumption per core as you have today, and it would run at about 4 gigahertz. Unfortunately, packaging technology tends to move forward at very small amounts, about 5% to 10% improvement per year in terms of power dissipation. So that's not going to happen. Instead, what's going to happen is this bigger machine is actually going to have to limit the number of cores that are active, depending on where we get with packaging technology, somewhere between 46 and 56 cores. Unfortunately, that makes Amdahls Law a problem worse, not better. And what happens is you take these power limits. Here's a standard Amdahls Law curve. You see this, it gets flat out here. It gets flat because that's when you've hit the temperature dissipation limit of the chip. So you have a compounded effect because of this limit on how many cores you can ever have fully active at any given time. And that's causing all kinds of additional havoc as we think about next generation processors. So that's bad. So it's a good thing I'm close to retirement because, you know, I've been in this field a long time. I've had the best part. All the young people coming into the field, they're going to really have to slave. So what's left? Well, there's software-centric mechanisms. Today, we all program in modern scripting languages. Python's very popular. Other things like that are very popular, Ruby on Rails things. They're dynamically typed. They encourage reuse. The good news is they've boosted software productivity. Programmers, they're horribly inefficient for execution. And I'll show you, by horrible, I'll show you some numbers. Hardware-centric approaches. Well, we're at the end of the road for doing this as general-purpose processors. We're not going to be able to design things that are as general-purpose and get forward. Accelerators are attractive, not just because they're interesting, but because there's no way you're going to build a general-purpose processor that continues to achieve the kind of performance improvements that we need. So we have to go to things that are more domain-specific, that take advantage of particular structure in the program to try to make things run much faster. And I'll show you some examples. And there's a combination of the two. We could have domain-specific languages with domain-specific architectures that make both improvements in how the language gets compiled as well as the architecture. So here's a great example. This is from a paper from a group of colleagues at MIT that's going to appear in Science. They take one application, admittedly a very simple application, a matrix multiply. And they initially write it in Python, and then they rewrite it in C. The C version runs 47 times faster than Python. Okay, now, I started my research life as a compiler person. Compiler people kill for factors of 2. A factor of 47 is like nirvana. So there's an enormous, if you could just go and make that go from an efficient Python program to an efficient C program, you could have a dramatic improvement. But then they go a step further. Then they say, well, if you take advantage of parallelism in an Intel multicore, and this is an 18-core machine they did this experiment on, you can get another factor of 8 performance improvement. And then if you lay out memory correctly so that the caches get used correctly in these machines, you can get a factor of 20, almost 20 from that. And then finally, if you make use of the SIMD vector instructions that are inside an Intel processor, you can get another factor of 10 out of that. So the end result is that the program runs 63,000 times faster than its original version. Now, 63,000, that's a lot of Moore's Law transistors, 63,000. So if you could get that, that would be great. You don't have to get it all. I'm sure if you got a factor of 1,000, people would be very happy, right? So there's a big opportunity here to think about how we improve the way we write software, and the key will be find ways to do that that doesn't give up some of the advantages we've gotten by going to these very powerful programming languages. What about hardware? Well, we can achieve much higher efficiency by trying to tailor our computations, our architectures, to more specific kinds of applications. We're not going to try to do every application. We're going to try to do a class of applications, and we're going to try and tailor the architecture to that class of applications to make it run fast. Obvious examples, neural network processors for machine learning, graphics processing units for graphics or virtual reality are obvious examples. The one piece of good news is that these are areas where people care a lot about performance and have a lot of demand. I really do not need to run Word any faster. In fact, I need it to have less features because every release, I get confused. Things move around. They change here. There's this new feature. Too hard, too hard. I need less, not more. So I don't need to do a lot of those things faster. In fact, maybe email coming in slower would be a good thing. I need more smarts, more really things where I can apply computers in new ways. Now, can we do better? Well, to start to think about that problem, maybe one way to start and say, where does the energy go in a traditional processor? What consumes all that power? Well, the first thing you'll notice is these are 8-bit integer adds, 32-bit integer adds, floating point multiplies of 16 and 32 bits. The number of picojoules they require is pretty small. In fact, look at this line. This is a 32-bit add, 1/10 of a picojoule. Just accessing a register file takes 60 times as much energy. Accessing a first-level cache, takes 100 times as much energy. So clearly, if we can slide the architecture and the programming model towards something that uses these energy-cheap kinds of instructions and avoids these energy-expensive instructions like an off-chip DRAM cache access, we can get a tremendous amount of improvement. 10,000 times to go off that chip to go out to DRAM versus do a 32-bit add. So there's a tremendous advantage in terms of doing that. And we'll try it. And of course, a lot of this has happened. I mean, we build these caches because they are much more energy efficient than going out to DRAM, right? We have register files because they're more energy efficient than going to caches. But we've got to rethink that problem harder. So just to show you the breakdown, here's a breakdown that you would see on a typical multi-core Intel processor or AMD processor in terms of an instruction which loads a register from a first level cache. Roughly half the energy is in control. Then the next here are the D cache and L cache accesses, and there's the register file access. So lots of overhead associated with it. Same thing if you look at a floating point, 32-bit floating point multiply that accesses the registers, so it has an L1 instruction cache access. The floating point multiply is a relatively small piece of the power, register file access, and again, a big control piece. So maybe we can find a way to get rid of some of that control overhead and improve the energy efficiency. So why can these domain-specific architectures win? So if you know anything about the work that Dave and I have done over many, many years, our work is characterized by we want to see a quantitative explanation of why something works and not a qualitative argument. So what are the quantitative insights behind why this can work? Well, the first thing is we move to a simpler model for parallelism. Instead of these out-of-order, complex architectures that try to find the parallelism in the instruction flow, we move to a system that's based on VLIW kinds of, or SIMD kinds of things, where the compiler, the software system, finds the parallelism and shows me where it is and structures the program appropriately. We try to make more effective use of memory bandwidth. We go to user-controlled memories versus caches. Caches are wonderful, except when they don't work. And they don't work for some particular class of applications. So we try to think about a different way to use on-chip memory that's more efficient. Eliminate unneeded accuracy. So IEEE floating point is great if what you care about is the ultimate in precision and definition. It's terrible if you care about efficiency. It has a lot of accuracy, but if your problem doesn't require that much accuracy, you still pay for it. So we move to systems that use less precision, that use shorter integers rather than bigger integers. And then finally, we move to a programming model that matches the architecture. And this is critical. We're not going to take random C programs and compile them for machines that have SIMD, that have user-controlled memory structures, and that have lower accuracy and make the programs run great. We're going to take programs written in a language for a particular class of applications, and we're going to match them to those architectures very efficiently. So that requires a domain-specific language. And what you do in these domain-specific languages is you don't start with Python or C. You start with a language that if I'm doing linear algebra, if I'm doing matrix operations, it says I'm doing a matrix operation. This is a matrix operation, right? It's a matrix multiply. It's a dot product. So I move to that higher level model. I try to avoid things like aliasing, which makes it essentially impossible to do user-level memory management. So you move those things out and you say, those are out of the language. If you need that kind of property, you need to write it explicitly so the compiler will not do the wrong thing. And we have languages like that, OpenGL, TensorFlow, P4, and lots more coming along. And there are interesting compiler problems here as well to be solved. So what about, if you're going to build a domain-specific architecture, what application space should you go after? Well, there's an application space where the number of papers being written is growing as fast as Moore's Law. And that's deep learning. And this just shows you the rate at which papers are being published plotted against Moore's Law's growth. And they are being published at that rate. So this is, we're standing in the aftermath of this tremendous breakthrough. Those of us that are old enough realize how many times AI didn't make that breakthrough till all of a sudden it happened. All of a sudden it happened. And it happened, by the way, because we got two things: massive amounts of data for training and massive amounts of compute power. Both those were necessary, and we were off by factors of 10,000 to 100,000 in terms of what we needed to make this technology work. But now we have it. So all of a sudden you've got tremendous demand for these compute cycles. And these are very well structured problems. So you can begin to think about building a machine for those. And here's one example, the Google TensorFlow processor. So it's an architecture designed to do the inference part of machine learning, not the training part. Machine learning has two parts. You train it, and then you do inference. So inside a self-driving car, inside a device that does adjustment of photos like this, you purely have an inference-based problem. And this is the first generation machine. It's built to do inference. It changes the way, it doesn't look at all like a conventional processor. It looks rather different. Uses large amounts of on-chip memory rather than caches. It uses a big matrix multiply unit. A matrix multiply unit that does 64,000 8-bit multiply accumulates every clock cycle. So enormous bandwidth throughput in terms of 8-bit multiply accumulate. And if you look at it, this shows you roughly what the area plot looks like on the first generation TPU. But what I want to look at is this comparison. So this shows you the use of die area, transistors, on a TPU-1 versus what they are on a Skylake core. So modern Intel microprocessor, but just looking at the core. So here you see 44% of its memory, 33% of its cache. Remember, with cache, there's additional overhead over memory because you've got to keep tags and other things. So more memory, lots more compute. 39% of the area of the chip is compute. That giant matrix multiply unit is a big piece of it. Here, only 21% is compute. Here, in the Intel processor, general purpose processor, 30% is control. Here, only 2% is control. So by going to a VLIW SIMD structure, we dramatically simplify the amount of control in the processor. And that really drives it. So a lot more compute throughput and more memory. So the result of that is you get significant improvements, particularly when you look at performance per watt, right? How fast is it? How fast is the processor per watt of power? That's an energy measure, right? Performance per watt is equivalent to energy per computation. How does it compare to either CPUs or GPUs? And it gets a significant improvement over both. Even bigger, obviously, over CPUs than it does over GPUs. And of course, these comparisons, there's some caveats with them. The GPUs are floating point, TPUs are integer, so there's some exaggeration or some advantage that comes from that comparison. But the results clearly indicate you can get much more efficiency by moving to these kind of domain-specific machines that are tuned for the particular architecture. This is a really interesting plot. These are things called rooflines. And what they do is they plot the peak performance that a particular architecture can achieve depending on what we call the operational intensity. That is, how many operations can you do per piece of data that you bring into the processor? And these are only useful for very large problems where you constantly have to bring data into the processor. So the roofline has two parts. It has this part, right, the eave of the roof, and this is limited by the memory bandwidth, how much memory bandwidth the processor has. And then it has the flat part of the roof. And the flat part is where you're limited by your computational throughput, either integer or floating point. How fast can you operate on data that you have inside the chip and you have to multiply, add, or do some other operation? So this really indicates why the TPU wins over the GPU. Namely, it has lots more computational bandwidth. So it's able, rather than go flat out here, it's able to go much further out in terms of performance using its computational bandwidth. Why is that such a good idea? Because remember that chart that I showed you, computation is much, much cheaper than memory access from a power point of view. So you gain a lot of energy efficiency by moving out and trading off and getting more and more computational capability. Okay. I'll make a couple points here about training. So the training is the counterpart to inference. Training is anywhere from 10,000 times to 50,000 times more compute consumptive. Training is a really hard problem because you have to solve big partial differential equations basically and do relaxation on them in a highly dimensional space. So it's a much harder problem. If you look at it, some of the early machines, AlexNet down here, AlphaGo, which became the world's Go champion, needs 300,000 times the training power of some of the early on neural networks. So enormous amounts of consumption of power. So the key idea then is build a machine that aims at training. But again, take the same philosophy and move in the same direction. So build machines which have lots more computational capability. Go to a 128 by 128 memory unit. And in the latest version of the TPU, the version 3, there are 2 of those on every single chip. This is actually a liquid-cooled chip. You see this little loop here? That's to run cold water through, so you can cool these individual chips. So even there, you're running into thermal dissipation limits. This is not something you're going to carry around in your laptop or your phone, right? Unless you want to carry a radiator on your back. You're not going to do that, right? So this is something you put in a data center where you have access to chilled water. But moving up this machine had a 92 teraops throughput. This has 180 teraflops, actually, because it supports floating point. And this has 420 teraflops with a vector unit. They also go to high bandwidth memory, these new memories that are packaged on the same substrate and allow you to get much higher memory bandwidth in order to do much faster computation. And then you can package these into big computing racks and build monstrous computing engines that are incredible compute power. So the TPU 3 is packaged into this big process like this where it actually has its on-chip interconnect already built in to the individual chips, so it can be wired up fairly easily. And this machine gives you over 100 petaflops in a space that is, about 1/40th the size of a typical supercomputer. And what about performance? So this is a fascinating curve. So what I've done here is taken, I'm looking at 2 different measures. In blue, performance. In green, energy efficiency. That is performance per watt, so energy efficiency. And here we take a number of different machines. Top 500 machines are the fastest machines in the world as measured on a dense LinPack problem. It's a linear algebra problem done densely. We compare those. Those are the fastest machines in the world. These are the fastest energy efficient machines in the world, called the top green 500. They're called green because they're more energy efficient than these big monsters here. And here's the 2 versions of the MPU built out of the TPU version 2 and TPU version 3. So you notice this has 2,000 cores. This is the fastest machine in the world. This has 2.4 million cores. 2,000 cores, 2.4 million cores. Look at the performance. This is within a factor of 2 of that machine. But look at its energy efficiency. It's more energy efficient than the top green 500 processors. So it has better energy efficiency than the most energy efficient higher-end supercomputers, while almost matching the performance of the very fastest machines in the world. Much more efficient, much higher levels of efficiency here. And that's key. That's what gives you this advantage. So this is a time now of lots of rethinking of problems, where the problems have changed dramatically. What we care about has changed. We're interested in these domain-specific machines, how you map these languages to the machines, how you deal with sparse data. One of the problems that arises is deep learning problems are all sparse. They're all sparse instead of dense linear algebra, and that's a much harder problem to figure out how to do. So you've got to figure out solutions to it. But it's also the case that as we move into this domain-specific area, rather than build one architecture which covers a very wide application space, we're going to have to build machines that are more tuned to particular problems we're interested in solving, which means we've got to make hardware design simpler, more like software design, easier to verify, easier to get designed. Because right now, to design a hulking big multiprocessor, Intel designs the next multicore from scratch, so it's a new microarchitecture, that's a 3-year, 300 to 400 engineer project. That's just, you can't afford that if you're going to have a lot more processors covering the design space. So we've got to figure out how to make hardware design a lot closer to software design, which means we've got to figure out verification, do a better job of verification, higher level design tools. What role could machine learning play in CAD tools? Good question. Machine learning is the ultimate thing for doing very complex optimizations. So it's quite possible you could do some interesting things. And then hopefully, I'm still hoping that somebody will come along and fix silicon and give us 20 more years of Moore's Law and all that. That would be great. And maybe some of the alternative technologies, packaging. Can you enhance cooling? Can you do optics? There are some ideas there floating around that. And then beyond silicon, carbon nanotubes, quantum. It's just a question whether nuclear fusion or quantum is going to come first. I can tell you they're both 10 years away at least, right? So we've got a ways to figure that. We've got time to figure that out. When they start talking about 5 qubits, I'm still waiting. So it'll take a while. But it's fascinating technology. The physics will be interesting no matter what. So this is a great quote in thinking about this. This is a quote by Dave Cook, who worked on a very famous machine, the Iliac 4, circa 1975, one of the first big SIMD parallel machines. Famous machine that was built. And there were a lot of people working on this, a lot of hardware designers, state-of-the-art technology, and there was one software architect by the name of Dave Cook. One software architect. And what Dave said is, these hardware guys built this great machine, but we couldn't figure out how to program it. And that's what we have to avoid in this domain-specific time. We can't have architectures that software people can't program and can't move their software to. So instead of kind of saying, well, we do the hardware over here, we do the software over here, and on occasion we let them talk to one another, we're going to have to think about a much more integrated approach, much more vertically oriented teams where people understand something about applications and the compiler and language system and the underlying architecture, and are in a dialogue across that vertical stack, rather than subdivide the stack and everybody optimize their own piece without talking to anybody. That's a big change in how the industry approaches the problem and thinks about it. But that's what's going to make it work. And if we can do that, at least for some really important problems, we can deliver dramatic performance improvements and keep the magic that we've created over the last 40 years going for a few more generations. Thank you for your attention. I'll be happy to answer any questions.
Very interesting. How many I'm not sure I got the architecture right. How many might there be?
Yeah,
are you talking about hundreds or thousands or millions?
I don't think there are hundreds of thousands or millions. I think there are classes of problems that are very important that you can break down into it. A lot of things will come back to mathematics. I mean, basically, deep learning is basically on inference. It's basically sparse linear algebra. Sparse linear algebra with relaxation in terms of training. So it's a class of things you need to do. Just as many scientific problems are dense linear algebra problems. So those are two big classes. Graphics, we already know. I mean, we have GPUs. That's a class that solves certain graphics problems. You can imagine versions of GPUs that are more oriented for doing VR or AR or something like that. But I think you'll see, obviously when you get to devices like this, you know, the chip that's in here that does the machine learning that gets used for the camera, it's specialized for that purpose because it's critically important and there's enough volume to justify it. But the domain is similar. The domain is similar. 50, 100 different domains maybe, with maybe several different kinds of processors spanning a range of power across that domain. Yeah.
Yeah, what do you think of reprogrammable chips such as FPGAs as opposed to a way of making it easier to design hardware?
Yeah, I think FPGAs certainly do improve ease of design. They're also the great prototyping technology. And in fact, one of the things that Microsoft has done is they've fielded these processors in the cloud using FPGAs that are designed particularly for deep learning kinds of problems. And the reason they did that is because their view is the algorithms are still under a lot of change, and rather than bind the hardware architecture, we can put an FPGA in there, and then 6 months later there's an algorithmic breakthrough, we can put it in. So I think that's good. They're not going to be the most energy efficient solution inherently, right, or the most silicon efficient solution, and that's the trade-off. But early on, they do have this advantage of flexibility, and I think that is a real advantage.
Okay.
So up until Amdahls started falling apart with the mainframes going out of business, I was writing software to run testers for the large boards and unpopulated boards, everything. And I'm curious about the implications for these changes that have happened and the changes you're foreseeing in actually testing this stuff.
Yeah. I mean, testing and verification both are critical problems. If you're going to design, if you're going to have more chips out there, right, as opposed to, you know, Intel releases the processor and sells gigantic volumes of it, you're going to have to improve the testing and verification problem. Now, there's some interesting things there. It turns out that test generation is related to a computationally very deep, complex problem. It's related to what's called 3SAT. It's an NP-complete problem. But test generation is a version of it. It has embedded in it that problem. Well, so some people are working on machines which do the 3SAT problem very efficiently, large-scale 3SAT problems. They could be used as very fast ways to do test generation, for example, and get greater coverage. And obviously, we're going to have to do a lot more testing, and we're going to have to do a lot more about security, and I didn't even touch on Spectre and Meltdown, right, which are problems that actually arise from speculation and so-called side channel attacks, things we didn't even think about. So there's going to have to be a lot more emphasis on that particular area, no doubt.
Maybe one more question.
One last question.
So if someone builds, like what you were saying, you know, in domain specific for crypto, then are we suddenly at risk because everything could get, you know, basically unencrypted?
So there is an organization that has built highly specialized architectures for crypto. It's in Fort Meade, Maryland. It's called the NSA. And there are things in Cray architectures and other supercomputers which are designed to accelerate exactly the problem they're doing. Now, the good news is all our modern cryptography technologies are built on RSA algorithm. The RSA algorithm uses a problem factoring very large integers. The funny thing about this problem is nobody knows how to do it quickly, but nobody knows how to prove that there isn't an algorithm for doing it quickly. Right? It's not what we call an NP-complete problem. It's not known to be exponentially hard, but there is no better solution known. One of the unfortunate things is that it is a problem for which there is a good quantum algorithm. So if we ever had very large quantum computers, but very large, much, much larger than today, you need about maybe a few thousand logical qubits, which probably you need 1 million physical qubits, right? So the biggest machines in the world are 72 qubits, so we're a long ways away from that. But that problem can be broken on a quantum. So if anybody ever figures out how to factor very large numbers very quickly, right now the classical, remember when you did figuring out if a number is quantum by building sieve of Eratosthenes? That's still the most effective algorithm. So, but if anybody ever figures it out, end of current cryptography. Now there are things called elliptical cryptography schemes that use elliptical curves and things like that that are quantum safe. So that's what everybody's trying to push towards. And I think they'll get them in time before somebody makes a breakthrough. Well, thank you for all the great questions, and thanks for coming.